welcome to the 7th lecture of the course Turbulence. So, before I proceed with today's discussion, so let us just briefly recapitulate whatever we have learnt in the last class. So, in the last class mainly we have talked about averages, for example, time average and ensemble average, and as you can remember that time average which we defined as that bar, and this is nothing but it is 1 by t integral t naught plus capital T u of t dt. This is what is our time average, and then we have talked about ensemble average, which is also defined as 1 by n 1 to n, then your this u I of t, this is nothing but I goes from 1 to n. So, this is I goes from 1 to n. So, this is what is ensemble average. Then we have talked about variance. So, variance of a random variable is nothing but its mean square, its mean square value is known as variance of that random variable. Then square root of the variance is known as RMS, and when we are talking about the RMS of a fluctuating quantity after removing mean, then we are calling it standard deviation, right. Then we talked about correlation. Okay. So, correlation, as you can remember that we defined correlation R of tau is equal to your u of t and u of t plus tau. Okay. So, tau is the difference in time. Okay. So, this bar means is the average. Okay. Then we have talked about spectra, and spectra we showed that that u RMS square is equal to minus infinity to infinity s of omega d omega. Okay. So, this is what we could find in the last class. Okay. So, little bit left out. So, we have only talked about the correlation with time. Suppose that that quantity, this I think we have considered the fluctuating quantity, that prime quantities. So, instead of this, if it is let us say function of just space. So, let us say if it is just a function of space, then that R of instead of tau we can call it R of s, and that we can define as u prime of let us say some x naught plus x naught and u prime x naught plus s. S is the separation in space, right. So, if u is a function of only one spatial variable, let us say x, then we can define this as this. So, in that particular case we can write our that s that energy spectra, or that s of instead of s of omega, here we can write s of alpha. Alpha is the wave number. Okay. So, which is nothing but spatial frequency. Okay. So, that is what I have told you earlier. So, s of alpha is nothing but your 1 by 2 pi, then minus infinity to infinity epsilon minus I alpha s and R of s ds. Okay. So, provided your u is a function of only one space variable. Let us say for general case, u of prime can be a function of x, y, z, or it can be a function of vector quantity, right. So, in that case, so this is not complete. So, in that case R of s just let me complete this. R of s is I alpha s and s of alpha and d alpha. Okay. So, these are known as Fourier transform pair, that is what we have talked about, right. So, now if this is a that u instead of function of x, u can be function of x, y, z. Okay. All three spatial variable u can be or u prime can be function of all 3 spatial variable. So, in that particular case we can define S of we can define this particular wave number vector k 1 by 2 pi cube, then minus infinity to infinity epsilon minus I k into x, okay, or here let us say that S is the spatial vectorial distance in the vector space or in the 3 dimensional space, then it is just a vector because it can be composed of delta x, delta y and delta z. So, k is our wave number vector. Okay. So, this into your that r of S, it is a function of S then, and it is ds. Okay. So, for a 3D case this is what is our definition, and this is the normalizing constant 1 by 2 pi for only one variable, since it is a k is a vector. So, k is basically alpha, beta and gamma. So, alpha is the wave number in the x direction, beta is the wave number in the y direction and gamma is the wave number in the z direction. So, in that case if it is 3D, then 1 by 2 pi cube, that is what is your normalization constant, and corresponding r of S r of S is given as minus infinity to infinity epsilon I k dot S, your S of k d k, right, it is a vector. Okay. So, this is what is your Fourier transform pair for 3D cases, and once again just like in the previous class what we did, instead of S we can consider to be 0. So, then it is becoming 0 means there is no distance. Okay. We are correlating a prime quantity with this prime quantity at the same position. Okay. That is what it means. That means this quantity is equal to minus infinity to infinity and this is 0. So, this is going to be decay, right. So, this is what is your energy spectrum, and this can be is nothing but your, if it is if this correlation is defined based on your u prime quantity. So, u r m s square is equal to this quantity, that is minus infinity to infinity s of dk. Okay. So, you see what does it say? Okay. It say that this is what? This is energy centered around that k, okay, and S of k dk it is the energy, okay, within wave number dk centered around k, right, because this is u prime RMS square. So, that is essentially velocity square. So, that is energy. So, this particular thing says actually S of k, it is a energy in 3D, correct, it is a vector in k. Okay. So, anyway this is the 3 dimensional analog, okay, whatever we have learnt in the case of temporal case. So, this is just a 3 dimensional analog. Now, if we consider this particular temporal expression once again, what we consider in the last class, if you can remember, one more result can be obtained. For example, the Fourier transform pair we consider r of S of omega is equal to, we defined 1 by 2 pi infinity epsilon I omega tau minus r of tau, right, d tau, okay, and its pair, if you consider this is a Fourier transform pair, then r of tau is nothing but your minus infinity to infinity epsilon I omega tau S of omega d omega, okay, this is where your r of tau is nothing but your u of t plus tau. Okay. So, this is the case we are considering, which we considered in the last class. So, one more interesting result can be found if we consider this particular integral, okay, and this is the Fourier transform pair, as you can remember from the last class. So, our S of w, you see S of w, or sorry, S of omega, it is not w, I very often make this mistake. Okay. So, 1 by 2 pi minus infinity to infinity, let me just write it separate, I omega tau r of tau d tau. Okay. See, let us consider the energy at omega is equal to 0, then this is, I can write 1 by 2 pi minus infinity to infinity, and this is r of tau d tau. Okay. And remember, this function is a symmetric function, that is what we have argued in the last class. So, that means this quantity can be written as u r m s square, you see u r m s square 2 pi twice 0 to infinity r of tau d tau u r m s square, okay, prime. Okay. Nothing, just some manipulation I have done. Okay. And now see, what is this quantity? It is a normalized correlation function, okay, capital R of tau. So, that means this equals to, can be written R m s by pi 0 to infinity capital R tau d tau. What is this? This is the time scale, right, integral time scale. So, this particular quantity 0 to infinity r of tau d tau, this particular quantity is known as time scale, integral time scale. That means, you see this quantity, that means this becomes energy at 0 frequency, it becomes u prime r m s by pi into the integral time scale, let us say t, capital T. So, that means energy at 0 frequency is proportional to integral time scale. Okay. So, keep this in mind. Okay. So, this is simply we have obtained from this keeping or putting the value of frequency to be 0 in both the side of this equation. Anyway, so our integral time scale is defined as 0 to infinity r of tau d tau. Okay, keep it in mind. So, this is a measure of the biggest scale in time in a turbulent flow. Okay. Similarly, you can define a length scale based on this correlation, spatial correlation. Let us say you have a correlation. So, in spatial correlation, this is instead of r of tau, if it is r of s, okay, ds, then this is the definition of integral length scale. Okay. So, this is known as integral length scale. Okay. So, this is, if you plot this correlation function in a turbulent flow, okay, if you plot the correlation function in a turbulent flow, it is going to come like this. Let us say it is tau, it is a temporal correlation if you do, and this is r of tau, then this is maximum value, it is a normalized one, maximum value, it cannot go beyond 1, keep it in mind. Okay. So, this slowly comes down, it slowly comes down and becomes 0. Okay. So, when we are defining the integral length scale L, we are 0 to infinity that or integral time scale t, that is r of tau d tau. So, this is what is your r of tau function. So, essentially this is nothing but area under this cup, right. So, this is the length scale, that means if a turbulent flow length scale is huge, that means this integral value is going to be high, okay. That is what it says. Okay. That means for a when length scale will be very big in a turbulent flow, this correlation will be not coming 0 so easily, it will come like this. Okay. So, that means the length scale corresponding to this particular correlation is much higher as compared to the correlation compared to this particular case. Okay. Okay. So, that means if we plot the correlation coefficient, then that gives us an idea about the integral time scale or integral length scale. Okay. So, that means this is very important quantity to characterize a turbulent flow. Not only that, we will see little later, not now. From this particular plot we can also define something called Taylor microscale fitting a parabola around r is equal to 0. We can find a Taylor microscale which is nothing but distance between this. Okay. It is a parabola fitted to this r is equal to 0 near r is equal to 0. Okay. So, what are the things we have learnt till now? To find out the length scale or time scale of a turbulent flow, we need to find out the correlation coefficient. Okay. If you plot the correlation coefficient and integrate, then you can find it out integral time scale or integral length scale. Okay. This is one thing. Another thing we have learnt, this correlation function is symmetric. This correlation function is symmetric, that is what also we have learnt. Okay. So, this can this is one of the important thing in turbulent flow, okay, this correlation technique. Okay. So, as we go ahead with this course, we will learn more and more regarding this correlation. Okay. So, you start thinking about what is correlation the way I have tried to explain in the last class, then you will better understand. Okay. So, all right, with this let us start something new topic today, and today we are essentially going to talk about Reynolds averaged Navier-Stokes equation. Okay. So, let me just before going to this new topic, let me just summarize whatever we have learned till now. Okay. So, till now whatever we have learned that turbulence is a property of a flow, it is not fluid property, and it is characterized by some properties. For example, turbulent flow is random, nonlinear, it composes of highly fluctuating vorticity, it is highly dissipative in nature and highly mixing, okay, or diffusive. So, these are the kind of properties of a turbulent flow, and we have also learned that the turbulent flow suddenly does not come in a flow. Okay. So, it does not occur immediately, there is a clear path the way it gets generated. Okay. One of these is actually instability, or the main the way turbulence get generated is the is due to the instability in a flow, and due to this instability what happens, a small amplitude perturbation can grow in a flow based on the parameter space, and that growth in the perturbation can trigger nonlinearity, which may take the flow to some other quasi steady or chaotic state, which eventually invites turbulence in the flow. Okay. And since that turbulence is highly random in nature, we have to consider the statistical tools to measure it or to kind of study the flow. Okay. So, that is what we have talked about in the last class, okay. Some of the statistical tools. Okay. So, that main point that turbulent does not immediately come in a flow. Okay. That means, if we consider a shear flow velocity profile and if you just add a small perturbation in a flow, suppose without perturbation your velocity something like this, it is always constant with time or steady, it does not change with time. So, then what do? You add a small perturbation. Okay. If you add a small perturbation about this basic state. Okay. So, this is your basic state, you add a small perturbation, then this one then your u plus u prime, you have added a small perturbation, and based on the parameter space what it may happen, this perturbation can grow with time or space, and this growth can initially invite the turbulence or generate turbulence in a flow, and that particular state, if you consider your that particular state, then that will be highly random in nature. So, this is what is your final turbulent flow signal, this is what is your time. So, this is your A, this is your B, this is your C, and this is your D. So, the D is the flow variable or velocity variable in a turbulent flow, right. So, it shows that is highly random in nature. So, that means we have to use some kind of statistical tools to quantify these fluctuations, and that is what we have talked out in the last class. Okay. Now, one thing, in fact, although the turbulence is highly fluctuating in nature, but any variable in a turbulent flow satisfy the Navier-Stokes equation. Okay. But that is not going to help us, okay, because it is highly fluctuating in nature. So, what is our intention? Our intention is to have a mean equation. Can we have a equation which can give us the mean flow characteristics? That is what is our aim. Okay. So, with this aim, if we go ahead averaging the Navier-Stokes equation, what we will get, that is what is the topic of discussion. Okay. So, we are talking about something like something called Reynolds decomposition. This is what is our instantaneous velocity fluctuation at this turbulent state. Okay. So, now this fluctuation can be decomposed this fluctuation can be decomposed as mean, okay, mean plus the fluctuating part. Okay. So, from now onward we will stick to some notations. Okay. So, from now onward we will consider the tilde as the instantaneous variable. Okay. For example, if u is the velocity and tilde means it is instantaneous velocity. Okay. It may be a function of space, time, space and time, okay, instantaneous velocity, and we will consider the mean to be capital quantity and the fluctuating quantity we consider, because writing prime every time it is problematic. So, we will consider the fluctuating quantity to be u removing the prime, and u tilde is the instantaneous. So, this is basically this particular plot is nothing but your actually u tilde, okay, and this u tilde can be divided in two parts, one is mean plus fluctuating quantity. Okay. And one more thing we would like to consider in this particular discussion or in this course, that we will consider the flow to be incompressible, okay, with negligible body force and constant property flows as well as stationary turbulent flows. So, mainly we are going to discuss about these stationary turbulence flows in this course. Okay. So, with this let us proceed. Okay. So, if we consider the equation your incompressible or Navier-Stokes equation, then our continuity equation is this, okay, and our momentum equation okay. Let us call this equation number 1 and this is equation number 2, okay. And here our consideration is that the flow is incompressible, gravity is negligible, with negligible body force, then constant property flows, means mu, rho all are constant, okay, and stationary. Flow is stationary, okay. That means its statistics does not change with time, that is what we have learnt in the last class, right. So, this is what our consideration, or this is what we will consider in this course, okay. So, first we will start with the what is our aim. So, this equation satisfy the instantaneous velocity, okay. So, this set of equations, so there are 4 equations here, one is continuity and 3 momentum equations. So, here one more thing, we will use this initial notations in this course. Here you see I and I both. So, I is repeated index in this particular case, okay, and here you see I is not repeated in any of the term. So, in this particular case I is free index and j is repeated. So, j is dummy index, j is dummy index or repeated index in the equation 2, okay. So, the index which will repeat twice, that is known as repeated index. And one more thing to keep it in mind, in any tensorial term we cannot have a same index repetition thrice, that means j, that is wrong. If anything coming like of that sort, that means you are making some mistake somewhere, that please you note, okay. And to learn this particular stuff, I have already mentioned you that you please go to that Kundu and Cohen book, and there is a chapter devoted to these notations, kindly read that, okay. So, this is not that very difficult to handle with. So, once you will practice along with me in this course, you will be able to pick up very quickly, okay. So, anyway, with this free index I in this equation, that for I is equal to 1 we will have one equation, for I is equal to 1 j will be thrice, that means I is equal to 1, this term will be 3 terms will be there, because j 1 there will be one term plus j 2 another term, j 3 another term. So, there will be 3 term, and when there is repeated index, that means that summation is implied, that is what is Einstein's summation notation, okay. So, when this repeated index is present, means your summation is implied. For example, this equation means del u1 del x1 plus del u2 del x2 plus del u3 del x3, okay, because I is repeated index and summation is implied. Okay. So, that is what the basic understanding which we need before we proceed, alright. So, now we will start with the continuity equation. What is our aim? Our aim is to find out a equation which will help us to calculate the mean quantities in a turbulent flow. For that only this exercise is going to be. Okay. So, now let us start with this continuity equation and let us try to find a average continuity equation and what we get in the process, let us see. Okay. So, this is what is your continuity equation. Let us take the time average of this. Okay. So, if you take the time average, what is the time average? T naught, which is the origin of time, we are starting the averaging, okay, 1 by T, okay, and dt. Okay. So, that is what we get from the continuity equation, right. If we take the time average of this equation, this is what it comes, and this means what? This implies that what we can do, 1 by T naught plus capital T, and you can actually del xi and use this decomposition. What is this? ui tilde means it is our instantaneous velocity, which include both mean plus fluctuating quantity. That means we can divide that particular value in two part, ui, capital Ui, which is our mean quantity, small ui, which is our fluctuating quantity, into dt equals to 0. Okay. Now, let us write the next step, or we can write del xi 1 by T, because this integration and differentiation which is commutable, that is what we have learnt in the previous class. Okay. T naught plus capital T, and here then our ui plus small ui dt is equal to 0. Okay. Or what we can write, del xi, right, 1 by T naught plus capital T capital Ui dt plus 1 by T naught plus capital T u of I dt is equal to 0, right. Or this is what? This is the average of this mean quantity, and we are talking about the stationary turbulence. In stationary turbulence, mean does not change with time. That means, this integral is going to give us what? U is constant, then U will come out T naught plus T. So, dt, that is nothing but capital T. So, capital T will cancel out and we are left with ui itself, plus what is this? We have learnt already in the last class, the value of this quantity, the average of any fluctuating quantity is 0, keep it in mind. Okay. That means, the value of this, that is ui bar, this is nothing but ui bar, which is equal to 0. So, average of this particular quantity is 0. So, you are left with this is equal to 0. So, it says, so this is our equation 3. Okay. This is our equation 3. So, what was our equation 1? Our equation 1 was ui tilde del xi is equal to 0. That was what our equation 1. Now, you see, we can write equation 1 as, without taking the time average, we can write this as this. Okay, ui tilde is nothing but is this, is equal to 0, or this equation can be written as zero. Now, from the time average of this equation is found to be what? From equation 3, this is what is equal to 0. or is equal to 0. This come from as del capital UI del xi is equal to 0 from equation 3, right. So, what does it say? It says the very important conclusion is that this exercise says the mean flow satisfy continuity equation as well as your fluctuating velocity or velocities also satisfy continuity equation. Okay. This is this needs to be kept in mind. Okay. So, this is very important point, all right. Okay. Now, let us consider the momentum equation. Okay. So, this is what is our momentum equation. Okay. This is what is our momentum equation. What we would like to do? We would like to take the time average of this equation too. Okay. So, if you would like to the time average of this equation too, so we can write taking of equation 2, we get what? So, tilde bar, this means we are taking the time average of this equation, bar means. Okay. So, uj tilde del ui tilde del xj bar minus 1 by rho del p tilde del xi bar plus mu del 2 ui tilde del xj del xj bar. Okay. Time average is distributive, that is what we have learned in the last class. So, if we take time average left hand side, that average is average the time average of the entire left hand term is equal to the average of this term plus this term. Similarly, in the right hand side, all right. Before we proceed further, here's what we have to do, we have to plug the the instantaneous, we have to replace these instantaneous variables with Reynolds decomposition. That means, Reynolds decomposition is uj is equal to capital Uj plus small uj. Okay. Similarly, for p, similarly for u and p. Okay. So, all right, before I proceed, some of the definitions which are very important at this stage, let me do this. Okay. So, in a side note, what I would like to mention, our Navier-Stokes equation, this del t plus uj tilde del ui tilde del xj equals to minus this minus 1 by rho del p tilde del xi plus nu del 2 ui tilde del xj, this particular equation we can also write as one by rho sigma tilde ij del xj. Okay. What is sigma tilde ij? That is stress tensor. So, that is nothing but is our p del tilde delta ij plus twice mu s tilde ij. Okay. So, s ij, So, here this is your stress tensor, okay, which includes stress due to pressure as well as viscous both. Okay. Delta Ij it is a basically Kronecker delta when I is equal to z is 1, otherwise it is 0. Okay. So, that is what it means, and Sij here Sij tilde, anything tilde means instantaneous quantity, that is what we need to understand. Okay. Sij tilde means capital Sij plus small Sij. Okay. Capital Sij means mean strain rate tensor, fluctuating strain rate tensor. What is mean strain rate tensor? Sij is nothing but half del capital Ui del xj plus del capital J del xi, okay, and small Sij similarly you can write as half del small ui del xj plus del j del xi. Okay. Okay. So, this is very important, this decomposition. So, these are all sort of coming from Reynolds decomposition. Similarly, that sigma Ij tilde instantaneous quantity we can write in two part, one is mean that sigma Ij plus fluctuating sigma Ij. Okay. So, this is stress tensor, and that can be decomposed also mean plus fluctuating quantity. Okay. So, the mean plus fluctuating quantity is the mean in this particular case we can write as, okay. So, that mean sigma Ij is written as your minus capital P delta Ij plus twice mu capital Sij. Okay. And what is capital Sij? That is already mentioned. Similarly, your small sigma Ij is nothing but your small p delta Ij, that is a fluctuating quantity, plus twice mu small Sij. Okay. Without tilde means it is fluctuating quantity. Okay. So, this decomposition we should keep it in mind. Okay. So, essentially this equation can be written in this fashion. Why? So, if it can be found immediately. Okay. If you just put the value of put the value of this quantity, then we can we can go to this particular equation. That is why this particular equation can also be written in this particular fashion. Okay. So, please keep it in mind. Okay. So, this is just in a side note I would like to mention this. Okay. So, now let us come back to this particular equation, and what we will do, this is the time average, this is time average. So, we will say this is our term 1, okay. This is term 1, this is term 2, this is term 3 and this is term 4. Okay. So, we will calculate these averages one by one, and let us say this equation is our equation 4. Okay. That is what we would like to say. All right. So, if this is the case, let us see what we get. So, let us work with the term 1. Okay. What is the term 1? Bar del ui tilde del t. This is the term 1. What is this? It means 1 by capital T, T naught plus capital T, this quantity, right, del ui del t del ui tilde del t dt. Okay. So, this del t is equal to, we can write 1 by capital T, T naught plus capital T, then ui tilde dt. Okay. So, this equals what? Del t. This is what? As per the definition, this is nothing but your capital U. Okay. Capital U means the mean. So, time average of this instantaneous quantity is nothing but mean quantity. Now, we are considering stationary flow. That means, the time average with means the average quantity does not change with respect to time. So, this quantity is equal to 0. Okay. So, term 1 says that bar. So, that means from term 1 what do we get? We get this quantity. So, term 1 this quantity, the averaging of this is equal to 0. Okay. This output I have got. All right. Let us start with the term 2. Okay. So, what is our term 2? Our term 2 is uj tilde del ui tilde del xj bar. Okay. Bar means time average. That means essentially what we are doing, 1 by capital T, T naught plus capital T, and this del ui tilde, so uj tilde del xj dt. Okay. So, this is what we are trying to do it here, right. So, let us so this equals 1 by capital T. Let us keep this as it is. So, T naught plus capital T and do the algebra inside. So, this uj tilde means capital uj plus fluctuating uj, okay. This and this one also we can use the Reynolds decomposition, okay, del xj, okay. Then dt. Okay. Now, you see 1 by capital T, you consider there will be 4 terms, right. So, let us see what are those terms, capital T. So, 4th term we are going to get at uj del ui del xj plus capital uj del small ui del xj plus small uj del capital ui del xj plus small uj small del ui or del small ui del xj dt. Okay. That means, we can take the time average, this time average operation distributive. So, individually we can time average each and every term. If we do that, what we get? So, let me write it here, okay, one by one. So, you see time average of the first term, what is that? First term in the sense I would like to mean not the first term what we have already worked with, first term means here, this is the one I would like to mention. So, this uj del capital ui del xj, right, dt. Okay. So, this is what it is. So, what is this? This particular quantity, it is all capital U, it is not a function of time. This quantity for a stationary flow, it is not a function of time. That means, we can take this outside such that integration T naught to T naught plus capital T is nothing, 1 by T is equal to 1. So, that means, if we do the time average of this term, that is going to give us capital uj del ui del xj. Now, let us consider the time average of the next term. So, next term means here we have to replace with ui, small ui, right. So, time average of this quantity means what? See, this is it's not a function of time, you can take it out. So, time average of this. So, essentially you can write uj del xj is equal to 1 by t naught T naught plus capital T u I dt, right. So, it is a fluctuating quantity, average time average of fluctuating quantity is 0. So, that means the time average of this whole quantity is equal to 0. So, that means time average of this quantity is 0. Similarly, time average of this quantity you can show this is not a function of time, because it is del capital u I del x j, which does not depend on time. So, it is the time dependent is there with only that small u j, and it is a fluctuating quantity. So, its time average is going to be 0. So, that means this is 0 plus what is the time average of this quantity? Let us see. So, time average of this quantity means u j del u I del x j dt. Is it 0 or non-zero? This is very important point. Okay. So, here both the terms are function of time. This is also function of time, and the derivative of small u I is also function of time. Okay. So, both the term are function of time. We cannot take one term outside and do the time averaging on the single term the way we have done in the previous two terms. Okay. So, that means this time average cannot be 0, okay, provided that u and u j and u I are correlated. So, this with little bit algebra we can show T naught plus capital T. You see this term I can write is as u j del u I del x j plus u I del x j del x j dt. So, dt is there, keep it in mind. I have kept this term as it is, plus just I have added u I del u j del x j. This is what? Del u j del x I, this is just a continuity equation which is equal to 0. That means, I have added essentially 0. So, no changes of this. That means, with this modification, so this is what? Del u j del x I. So, del u j del x j, which is continuity equation. What is our continuity equation? Is this, right? And we found that if this is the case, our fluctuating quantity equation continuity equation is also this, and here I is what? I is repeated index. We can also write this as u j x j is equal to 0, same thing. We are just changing I here, because anyway it is repeated index. So, that means I am essentially adding 0 here. That means, I can write this as 1 by capital T naught plus capital T, and this quantity I can write is at, you see, a del u a del b del x and b del a del, okay, and b del a del x. Okay. So, that means, this 2 we can write as u I u j del, okay, x j dt. Okay. That means what? This is what? Now, this equals what? This I can, that del term or the derivative term I can take it out, x j, then I can write 1 by capital T naught plus capital T equals to what? u I u j dt. Okay. In a turbulent flow, when these two fluctuating variables are associated like this, they are correlated, they cannot be 0, keep it in mind. Since they are correlated, for any two fluctuating quantity you cannot make it 0. Okay. If any multiplication of this sort is present in a turbulent quantities, so you cannot make them 0, because they are correlated essentially. So, their multiplication cannot be, or their product cannot be 0. Okay. So, that means this particular quantity then what? This you can write as del u I del j bar. That is what the definition of this. So, essentially the second term time average is equal to time average of this quantity is this, time average of this quantity is 0, time average of this quantity is 0, time average of this quantity is going to be your del ui uj bar del xj. So, the time average of term 2 you have got. So, time average of this quantity you have got already. What is that? That means 0 plus uj del ui del xj plus del ui uj bar del xj. That is what we have got in the left hand side of this equation, right. Now, let us see other two terms which are left. Okay. So, now we are going to work with the term 3 of equation 4, and what is that? Minus 1 by rho del p tilde del xi, time average of this. So, by definition we can write T naught plus capital T is equal to minus 1 by rho del p tilde del xi dt. Okay. We are talking about constant property flows. So, we can take the rho out, and also so minus 1 by rho del xi equals to, we can write 1 by capital T naught plus capital T, and this is your p tilde dt, okay, bracket close. So, this equals, you see, minus 1 by rho del xi. What is this quantity? So, that is nothing but your capital P, right. So, average of this instantaneous value is nothing but your capital P. So, that is what it is. Okay. So, this is what is your capital P. So, this is the output of your third term here. Okay. So, the value of this quantity, so that means this equals value of this we have got 1 by rho capital P del capital P del xi, okay, plus we do not know what we are going to get with this term. Let us see. We will work with term 4. Okay. So, time average of term 4, that is nu del 2 ui tilde del xj bar. So, once again we can write this as 1 by capital T naught plus capital T nu del 2 ui bar del xj dt, right. And since integration and differentiation are interchangeable or commutable, we can write nu into del 2 del xj, okay, 1 by capital T integral T naught plus capital T ui tilde dt, okay, and this is once again what is that. I believe you can follow that, because I am just jumping one step here, because according to definition the value is capital U, right. So, that means we can also find that as this, okay, just like in the previous case we had write this and 1 by capital T naught plus capital T ui dt, and you see average of the fluctuating quantity is 0. this part is 0, that means we are going to have what nu del 2 capital U I x j x j. Okay. So, that is what we are getting. So, our fourth term after time averaging, we got what nu into del 2 capital U I del x j del x j. So, if we write it afresh, or we can write u j del u I del x j equals minus 1 by rho del capital P del x I plus nu del 2 capital U I del x j del x j. Let me write this as minus, let me take this term, look at this term I am taking in the right hand side. Okay. So, if I take this term in the right hand side, I can write this as u I u j bar del x j. Okay. So, this is what is our average momentum equation. Okay. Let us see what we got, okay. Or what we can write, you see, let us multiply by rho in both this side, then we can get minus capital P del x I, rho into nu is nothing but your mu del 2 U I del x j minus, I can write this term as minus rho U I u j bar, okay, del x j. All right. So, you see this is just kind of your mean flow variables. Along with that, we had got some extra term here. Okay. Let us see what it is. So, you see, if we would have got our average Navier-Stokes equation is just this, it's just this. Okay. If we would have got our average momentum equation is this, then along with the continuity which is this, we would have solved the system for mean flows. For example, u I, sorry, this should be u j here, I am sorry. Okay. So, that means here 3 momentum equation, okay, and 1 continuity equation, and total number of variables u 3 variables, p 1 variable, total 4 variables and 4 equations, 3 momentum equation and 1 continuity equation. So, total 4 equations, 4 mean variables would have solved the system. But right now what is the problem? The moment you are considering your I is equal to your I is free index, then you see here something is sitting minus rho u I j, and you will see it is having total 6 unknown, 3 diagonal terms and 3 non-diagonal terms in this particular tensor. So, that means instead of getting 4 variable and 4 equations, we have got 4 equations with 10 unknowns. Our number of equation is 4 only, because here now if you remove this, how many variables? 3 mean velocity, 1 mean pressure 4 and another 6 unknown here, another 6 unknown here. So, 4 plus 6 10 unknowns, but equation once again only 3 equations here and 1 equation here. So, 4 equations. So, actually we are unable to find a system of equation which can be solved to find mean variables in a turbulent flow till now. We are in trouble. To solve this set of equations we need 10 equations for 10 unknowns, okay. Otherwise we will not be able to find these solutions of these mean variables, okay. That is one problem we have arrived at this stage. We will see whether we can find another equation for these 6 variables or another 6 equation for these 6 variable here, that we will see in the next class. But today let us see what is this term first of all right. So, anyway let us see this particular equation. Now we can write as uj del ui del xj. See, I can write this term as del p del xi plus this term can be written as twice mu del xj capital Sij, okay. Capital Sij means the mean strain rate tensor, okay, half del capital ui del xj plus del capital uj del xi, okay. So, that is what it is. So, I can write plus whatever it is there, let us write as it is, okay, ui uj bar, okay, del xj. Now, the entire term in the right hand side can be written as del xj. I can write this first term minus p delta ij plus twice mu capital Ij minus rho ui uj bar, okay. So, you see this particular term we have already introduced. What is that called? Sigma Ij. We have already mentioned this is mean stress tensor sigma Ij. Sigma Ij is equal to minus p delta Ij plus twice nu capital Sij, which is mean strain rate tensor, this one. So, this is equal to sigma Ij, right. So, this is a stress plus some other quantity is there which is inside this stress only, okay. So, this is most likely is the stress. Why this is called stress we will come back, okay. So, this is also a stress quantity which is known as Reynolds stress, and why it is called stress we will come shortly to that, okay. So, essentially what we can say that this equation, or we can write p uj del capital ui del xj equals to, we can write del Tij del xj, and here Tij is the total turbulent stress tensor, which includes mean plus turbulent stresses. So, Tij total turbulent stress tensor, which is equals to P delta Ij plus twice mu capital Sij minus rho ui uj bar, okay. Okay. And this quantity, what do we say? It is a Reynolds stress tensor. So, this is tau ij, small tau ij is equal to, let us write rho ui uj, okay. And this is known as Reynolds stress tensor, okay. It is having total 9 component, because you see, if you see tau ij, you see minus rho ui square bar, then minus ui u1 uj, means j is equal to 2, I is equal to 1, and this is j 1 I 1 for the first term, I 1 j is equal to 2 for the second term. So, rho this minus rho 1 3 third term, and minus rho u I is equal to 2, j is equal to 1 bar, minus rho u2 j is equal to 2, I is equal to 2 bar, minus I is equal to 2, j is equal to 3 bar, then minus rho I is equal to 3, j is equal to 1, then minus I is equal to 3, j is equal to 2, okay. Then minus rho u3, sorry, rho u3 and u3, okay. So, you see why it is 6 unknown, because you see this, so essentially this and this, okay, same rho u3 u1 bar, same thing, okay. So, similarly this and this, okay, similarly this and this, and similarly this and this, okay, these two terms. So, it is symmetric, right. So, Reynolds stress tensor is a symmetric matrix, okay. So, that is why, so this one unknown, so this can be written as, you know, essentially instead of rho u2 we can write this as u2 square, which is nothing but rho u1 square bar means what? URMS square, this is VRMS square, this is WRMS square, okay. So, that is what it is, so square, right. So, you see there are 3 normal components and 3, you know, off diagonal components which are same. So, these off diagonal components, you know, take parts in the momentum transport, okay. So, this off diagonal component take parts in the momentum transport, whereas the contribution of this diagonal term in the momentum transport is not that significant, but the contribution of this off diagonal term in the momentum transport is significant. Since this, you know, takes part in the momentum transport, we call this quantity as stress, because if you remember that sigma 1 2 or sigma 2 1, you know, viscous stress, or this is equal to what? Del u1 x2, when u is a function of x2 only. So, this is what this stress comes from the molecular transport of momentum. Similarly, this also, you know, this momentum transport happens due to the fluctuating velocities in a turbulent flow, and we will see in the next class in detail how these fluctuating velocities are taking part in the momentum transport. So, that we can call this quantity as stress. Okay. So, till this let us stop here today, again we will start in the next class from this point onward. Okay. All right. Thank you.